Alright, so what we're going to do in this video is we are going to talk about formulating this market share problem as a Markov decision process. The description of this problem appears on the left. Essentially what we have is we have a company that can be in three positions within the market share. It can be in the lead position, the second best market share, and then the smallest market share. And each month the company makes a different amount of money based on what market share it holds. And then we basically have this situation. We have two choices in terms of our advertising for that particular month. We can kind of just maintain normal advertising levels, or we can implement an aggressive advertising campaign, which is going to cost us an additional $10,000 to implement. And what we're going to try and do is, we essentially have an underlying Markov chain where the states of the Markov chain is what position is our company in. And then we have decisions that we can implement in each of those states. So hence we have kind of a Markov decision process. So what we're going to talk about in this video is formulating this problem as a Markov decision process, and then talking about kind of formulating a linear program in order to help us determine the optimal policy of this MDP. So in terms of the Markov decision process, model, we need to identify kind of four things in order to capture this as an MDP. We need to identify the states, the decisions that we can implement in each state, the costs of being kind of the joint costs of being in a state and implementing a particular decision, and then also the transition probabilities, which are going to be dependent on our decisions as well as the states. So the states, it's kind of pretty clear that the state is what position our company can be in. So our states are, we're going to have state 0, which is we're in the lead market share. We're going to have state 1, which we're in the second market share, and then state 2 is we're in the smallest market share. And our decisions, we have two decisions. We have what we're going to call decision 1, and this is kind of just implementing our normal advertising. And then we have decision 2, which is this aggressive advertising. And now we can look at our costs. And what we're going to do is, we're going to kind of roll in our monthly revenue into the cost of being in a particular state. So we need to kind of basically have 6 combinations of states and decisions. One, basically in each of the 3 states, we can choose one of 2 decisions. We need to calculate the cost for each. Now, if I just maintain normal advertising, my quote-unquote costs are really the opposite, the negative of our revenues. We make $50,000 if we're in the lead market share. So from a cost perspective, we have a negative $50,000 cost. So our costs are C of 0, 1 is minus 50,000. Our cost of being in the second market share and continue with our normal advertising is minus 35,000. And then we also have our cost of being in the smallest market share and implementing normal advertising as negative 15,000. And then when we choose to pursue the aggressive advertising, so basically being in state 0 and choosing decision 2. So one thing I want to kind of emphasize is I probably should have written this down earlier, but we're looking at costs of CIK, where we're looking at the cost of being in state I and implementing decision K. So C02 basically means we're in the lead market share and we're choosing to aggressively advertise. Our costs are minus 40,000 because we have to factor in the $10,000 we're paying for the aggressive advertising campaign. Similarly, C12 is minus 25,000, and then C22 is minus minus $5,000 for our costs. So now we need to look at our transition probabilities. And our transition probabilities, we're looking at P under the probability of being in state I, transitioning to state J, under decision K. That's what we're really interested in obtaining. Luckily for us, these P's are pretty straightforward in this case. If we look at the table on the left here, that actually gives us all of the transition probabilities for decision 1. So for example, Pij of 1, Pij of 1, we can look at entry I comma j in the normal advertising table. And then so as an example, if we want to look at probability of transitioning from state 1, so the second market share, to state 0, the lead market share, under decision 1, this is going to equal 0.20, because essentially we have that in the combination of where I is equal to second market share, or I is equal to 1, and J is equal to the lead market share, we have 20% chance when we implement decision 1. And now this other aspect of things. So I mean, I'm not going to list all of these out. It's just really pulling in from this table. Second thing is, well, what happens when we implement the aggressive advertising decision? Well, it's a 50-50 chance that we end up in either the lead market share or the second market share. So in this case, what we have is P from any I into the lead market share to state 0 under 2 is equal to 0.50. And then P from any state to state 1 when we implement decision 2 is also equal to 0.5. So we have now at this stage set up our Markov decision process model. We've identified the states, we've identified the decisions, we've calculated the costs, and we've have a way or kind of determine what the transition probabilities are based on each of our decisions for each of our states. So now what we want to do is we want to basically figure out, well, what is the optimal policy for this Markov decision process? So what would we actually implement in each of our 3 states? And we also want to essentially determine the long run average cost, or the long run cost per unit time or per unit month. So what this requires us knowing is not only our policies, but also what percentage of time do we spend in each of the 3 states. So in order to do this, we're going to formulate a linear program model. So we're going to look at a linear program model of the MDP to help us determine the optimal policy. So what we have is we're going to define these variables y, I, k, and these variables are what we're going to kind of view as the joint probability of being in state I and making decision k. And what we're going to see, or what we have is the way we formulate this LP, we will only ever have one of these y's on. There's an optimal solution where exactly one of these yi's are, at most one of the yi's are on for each of our states. Whichever yi is on for state I, that gives us the decision that we will have implemented in that state. And then the yik for that particular decision becomes the steady state probability of that particular state. So essentially our objective in our LP, given these decision variables, our objective is to minimize our long run costs. So what we're basically looking at is we're taking the yiks and multiplying them by the ciks. So in this particular case, we're going to have minus 50,000 of y01 minus 35,000 of y11 minus 15,000 of y21 minus 40,000 of y02 minus 25,000 of y03, or sorry, not 03, y12, and then minus 5,000 of y22. So very simply, we're just essentially multiplying, taking the cost, multiplying by the decision variables. So now we have to look at, well, what are the constraints we're subject to? And there are a couple of sets of constraints, relevant. Essentially what we're looking at is we're kind of modifying the steady state probability constraints. So we're going to have constraints, one constraint for each state. And then we're also going to have the fact that if I sum up all the steady state probabilities, we have to equal to 1. So be equal to 1. So if we're looking at yik as the joint probability of being in state I making decision k, if I sum up all the possible state decision pairs, the sum of the y's have to equal 1. So one thing we can, our kind of first constraint is y01 plus y11 plus y21 plus y02 plus y12 plus y22, they all have to equal 1. The sum of them have to equal 1. So this is kind of the traditional constraint of, steady state probabilities have to equal 1. And then the next constraint we need, or the constraints that we need to look at, is now for each of the states, we need basically the joint probability, the probability of being in that state is equal to the probability of transitioning into that state. So on the left-hand side, what we need in this kind of, well, if I look at the steady state probabilities, I can look at, well, pi I is the percentage of time we're in state I, or the probability of being in state I. In this case, we don't have a pi I, but we can get pi I by adding up the y's associated with that state. So for state 1, we can look at y01 plus y02 gives us the the probability of being in state I. And then this needs to equal the probability of transitioning into state 0. So we need to look at all of the different ways that we can transition into state 0, and then look at, and when we're talking about transitioning to state 0, that includes kind of making what decisions can lead us to state 0 times the probability of that decision being implemented, or that decision leading us to that particular state. So one thing is, if we look, you need to kind of look at the columns of transitioning into the lead market share, into the state 0. Well, in this case, if I don't do anything, if I have my normal advertising, I can transition to the lead market share if I'm already in there with a rate of 0.70. And then I can also, if I'm in the second market share, so in state 0, I can transition to the lead market share with a probability of 0.2 as well. So what we have is we have a kind of our first couple ways to get to state 0 is 0.7 times being in state 0 and implementing decision 1. And then we also have 0.2 times being in state 0, being state 1 and choosing option 1 as well. And those are the two ways that I can kind of, under the normal decisions, those are the two ways I can end up in state 0. And then I also have, if we choose the aggressive advertising in any of the states, I have a 50% chance of ending up in state 0. So what this means is I need to include 0.5 y02 plus 0.5 y12 plus 0.5 y22. So again, the right-hand side, what we're basically doing, when we calculated the steady state probability equations, or looked at the steady state probability equations, we looked at what are all the ways I can transition into state I on the right-hand side of these constraints. And we're doing kind of the same thing, but now we not only need to look at the ways when we look at the ways we can transition in state I, we need to look at being in other states and the decisions we can implement to potentially get there. So for example, I mean, if I look at state 2, this being in the smallest market share, if I choose the normal advertising, I have a 0% chance of ending up in the lead market share. So that's why we don't have a term with Y12 in this equation. So this is kind of what I'd call the steady state probability equation for state 0. And then we have the same thing for the other states. So we look at Y11 plus Y12. That's kind of the probability of being in state I. And then we look at, or state 1, then we look at all the ways we can end up in state 1. And if I look at under normal advertising levels, I have a 30% chance of going from the lead to state 1, a 50% chance of going from being state 1 to itself, and a 40% chance of being the smallest and ending up in state 1. So what we have is we're going to have a 0.3 Y01 plus a 0.5 of Y11 plus a 0.4 of Y21. And then we have a 50% chance of being in, if we choose aggressive advertising, ending up in the second, in state 2 as well. So we have a 0.5 Y02 plus a 0.5 of Y12 plus a 0.5 of Y22. And this is the steady state probability equation for state 1. And then we also need a steady state probability equation for state 3. So we're going to look, or not state 3, for state 2. And then we have a Y21 plus a Y22. And then we need to look at all the ways we can end up in the smallest market share, state 2. I mean, really, if I implement aggressive advertising, I can't end up in that state. So we don't have any terms with decision 2 implemented and ending up in kind of state 2. So we really only have, we have a 30% chance if we implement the normal advertising in state 1, so Y11.3 plus a Y plus 0.6 times Y21. And this is steady state equation for state 2. And our last thing we have is that we have the YIKs are greater than or equal to 0 for all I and K. So a couple things to essentially point out in this. So this is kind of how the LP to get the policies. What happens if we solve this LP is that we have essentially what happens is we're only going to end up having 3 basic variables in any basic feasible solution to this problem. And the main reason that happens is that one of the sum of the y is equal to 1 constraint is, if you look at the set of 4 equations that we have, one of them is redundant. So what this means is that we only end up with at most 3 positive variables, positive y's. And what is interesting is that we have 3 positive y's and we have 3 states. So what happens is for each state, at most one of the YIKs can be positive, and whichever one is positive is the decision that we would implement in that particular state. So one thing I just kind of point out from kind of solving this problem is we should always make sure that we include, we could essentially drop one of the constraints, but we need to make sure that we include that the sum of the y's are equal to 1. This particular problem we wouldn't run into an issue with, but when we have costs, and if the costs are, instead of having a revenue portion, if we have positive costs, if we don't include the sum of the y's equal to 1, what will happen is it's feasible to just have all the y's 0 and still solve the problem. So that kind of concludes this video on formulating this this particular problem as a Markov decision process, and then formulating the LP for it as well.